Right, hello, Losic. Just answering a few of your questions that you had on the equilibrium exam questions that you did on Tuesday, I think it was. Tuesday? Monday? Tuesday. Sorry, I'm just waiting for my pen to turn on. Come on, turn on. Turn on. There we go. Good. So, first question is Roberto's question about question 1A, part 3. Why the units cancel for the expression Kc? Okay, so I think Roberta didn't ask about how to work out what Kc was or anything like that. So I'm assuming this is already knowledge. That Kc here is going to be the concentration of hydrogen iodide squared, because it's 2 times in the equation, divided by the concentration of H2 times the concentration of I2. Now, if we why do you first of all here, think about how you work out that the equilibrium has no units. So what do you do? Well, you're going to go, okay, so Kc's units are going to be equal to moles. Mole. So my right hand side of my screen is dodgy with the pen. Let's go on left. Kc is going to be moles per decimeter cubed, and you're going to square that on the top actually, because you've got the concentration of Hi squared, and you can divide it by, again, moles per decimeter cubed squared, because the mole per decimeter cubed is times twice on the bottom. This pen's annoying me, so I might even have to go and get another one. But let's see. Yeah, just bear with me. All right, there we go. This one should be better. Mole dm3 squared. So they're going to cancel out, and that's all you've got to put. State why the units cancel the equation. Well, you've got 2 concentration units on the top and 2 on the bottom. So they cancel out. Now, well, where did that come from? Well, that came from the equation. In the equation here, you've got a mole of hydrogen reacting with a mole of iodine to make 2 moles of Hi. So really, you've got to talk about the fact that the total number of moles of species on the right hand side is the same as the total number of moles of species on the left hand side, and that's all they're looking for. Next question. Question 2 was this compromised temperature idea. Now, compromised temperature is basically in industry you want to make as much money as you can, and you're trying to synthesize methanol here. Now, you've got to remember that there's 2 big things. One is how quickly you can make the methanol, and 2 is how much of your mixture, once you add these things together, is methanol. So and that's really what we call yield. So we have a yield consideration, and we have a kinetic consideration, and to be honest, we also have a kind of economic consideration as well, even more so when it comes to things like if you want to have a massive temperature, well, that's going to cost you in energy cost and in having equipment that can deal with high temperatures. Same with high pressures. Safety considerations with high pressures, definitely the pressure, the amount of energy it took to run the pumps to make the high pressures. So the compromise just comes from the fact that you have to compromise all these 3 factors: yield, kinetics, and other considerations, practical considerations, we should already call them, I suppose. And that's all it's talking about. So here, compromised temperature here, well, they're talking about the temperature, okay? So let's think about how the temperature, well, what temperature do we want, high or low temperature, to get a good yield? Well, good yield is going to be shifting in the right-hand side of this equilibrium. It's exothermic, so to make it go in the exothermic direction, that means it's going to be heating up. So I need to be cooling it down so that it's trying to oppose my change of cooling it down by heating it up. So yield, you want a low temperature. But reactions are quick if you have a high temperature. More collisions per second, and also a greater proportion of those collisions have energy greater than the activation energy. Those two reasons together means there's more successful collisions per second. So high temperatures want for that. So also practically, well, we don't want to pay for the high temperature. So practically, we'd kind of like it to be low if possible. Compromise between all these three factors is we're going to use something like 400 Celsius in this case. And you often see it's around there. I think that's a lot because of the practical regions. If you get higher than 400 Celsius, then you need to use a bit more specialist equipment, especially if you go into the high hundreds, or the thousands. I would say kinetics is a massively important thing here because actually we don't really ever go to equilibrium in these industrial processes, because why bother? You continually tap off your product if you can, and so. But the further you are away from the equilibrium, the quicker things are going to try and shift there. So it is an important consideration. But they talk about it as if you're going to go to equilibrium. But compromise, kinetic you want high temperature, yield you want low temperature. Let's meet in the middle, and 400 is kind of meeting in the middle there. That's all that means. Question 3b was questioned about as well. State how and explain why the use of catalyst might or might not change the equilibrium yield of hydrogen and also the amount of hydrogen produced in a given time. Okay, so time, when they say in a given time, then we need to think kinetics as well, i.e. rate of reaction. But they're also talking about equilibrium, of course, so we're going to be talking about yield. So let's keep ourselves organised. Talk about yield first. So catalyst, using a catalyst, does that affect the position of equilibrium, left-hand side or right-hand side? And the answer is no, because using a catalyst speeds up the forward and the backward reaction equally, because it lowers the activation equally for both forward and backward. Forward and backward equally. Okay, so we've stated how it changes the equilibrium yield. It doesn't. We've stated why, because it speeds up the forward and backward reaction equally. For 4 marks, I might be starting to think because it lowers the activation energy by identical amounts. I might start slightly defining what a catalyst is, though it doesn't. I think that probably isn't worth a mark. But if there's so many marks, sometimes it's worth just giving a very full answer. And also the equilibrium and the amount of hydrogen produced in a given time. Okay, so let's talk about kinetics. It does lower the activation energy. That means a greater proportion of collisions are successful. Greater proportion of collisions are successful, therefore faster. Faster reaction, because you said greater proportion of collisions, you should say have energy greater than the activation energy and therefore are successful per second. Very important thing to say, therefore faster reaction. So you produce more hydrogen in a given time. Okay, so look at the mark scheme, but that's going to cover definitely most of it, if not all of it. And then here, great question from here. He just had a thought about one of his, maybe one of his favourite equilibriums. I don't know how much he likes different equilibriums, but one of my favourite equilibriums definitely, which is water. What is water evaporating? Okay, it's there in equilibrium. You put you have your bag with your goldfish in it, and it's all sealed up. When you take it back from the fair, that the air above in that plastic bag will stay the same amount of moist, because an equilibrium will have been reached. A little bit like a sock of, the classic example of a sports bag all wrapped up tightly, where with some sweaty socks in. They're not going to dry out in that tightly packed up sports bag, although many reactions will happen to give off ammonia and things like that, but that's by the by. Right, why doesn't Kc change when pressure is changed for H2O evaporation equation? Okay, so Kc doesn't change when pressure is changed normally because the volume overall will will decrease as you increase the pressure, and that kind of cancels out whichever way you shift in the equilibrium. But for something with this is an extension question now, actually, because it talks about a heterogeneous equilibrium, which means that you've got a mixture of liquids and gases. The ones you're going to be asked about 90% of the time are going to be all gases or all aqueous things, or potentially all liquid things. But you're a lot less likely to be asked about heterogeneous systems. But the way to treat them actually is, if you think about what Kc is. Kc is in this case going to be the concentration of water gaseous divided by the concentration of water liquid. Let's just think about what that is here. That's the number of moles of gaseous water, H2O gas, divided by the total volume of the gas. So just volume of the gas here, and divided by the concentration of water liquid, which is the number of moles of water liquid divided by the volume of water liquid. So we could put that in as well. Although actually, I'm just going to go to the other pen again. Actually, I think the concentration of water liquid is quite a nice thing just to think about in its own right. But still, let's see if this pen's a little bit better. So number of moles of H2O liquid divided by the volume of the liquid. Now, the really big important thing here, you won't see this in the web because they simplify it straight away. The really important thing is here, actually, let's get a different colour pen. Actually, imagine increasing the pressure. You know what's going to happen if you increase the pressure, probably in this equilibrium, and that's going to be that the equilibrium shifts to the left and decreases the pressure by changing the gas to liquid and opposing my change of increasing the pressure. Okay, so we know the equilibrium will shift to the left if we increase pressure, but surely Kc shouldn't change because it's an equilibrium constant. It should only change when temperature changes. And it does work, because imagine you've got a little pool of water and then changing water gas into water liquid happens. The concentration of water, the number of moles of water in a certain volume of water does not change. You create more water, absolutely, but you don't suddenly force that water droplet that's already there to be the same size and force it to be more dense. You don't. It just gets bigger. So the volume of the liquid, because you've made more water, you're going to have a bigger pool of water. So the concentration of water does not change. Liquid water does not change, and that is why you will always see, if you look at these equilibrium heterogeneous systems, you ignore solids and liquids, pure solids and pure liquids, and they don't exist in the Kc expression, because concentration of water should be constant. Okay, so if it's constant, then it doesn't exist in this equation. If it's not going to change, you just make the equilibrium constant a different number, but never consider it in the first place. But the concentration of water gas would change, or would it change? That's the question. So, if you're increasing the pressure, well, that's going to decrease the volume. Increasing the pressure of you squeezing that bag, that's going to decrease the volume of the bag, the gaseous volume. But also that the number of moles of water, vapor, is going to decrease as well, because this equilibrium shifts to the left-hand side. And actually, Kc is kept constant by the number, when the water molecules condense, the number of water molecules that condense balances out the fact that you've got a smaller volume. So Kc is still actually a useful equilibrium constant here, because it can tell you how those two things are affected each other. So, like I say, you're really unlikely to get asked about equilibriums of heterogeneous equilibriums, but I thought I'd answer that anyway. Okay, and the good thing is nobody asked me any other questions, so hopefully that means we're all quite good at this section. The percentages look good, so well done.